Hello everyone, welcome back. In the first video, we talked about general machine learning pipelines introduced when we get the data, how to pre-process the data, what method we can use to visualize the data, and what are the available machine learning methods and to build the predictive modeling. We have situations, for example, like classification, regression, and also we can do unsupervised learning like cluster analysis. Also importantly, we also talked about how to evaluate your machine learning methods, how to design the experiments using cross validation, try to use independent data set if you have the resources. And also talk about different evaluation matrices to compare the performance between different methods, and also give some tips of the whole process. So if you haven't looked at that video, so please look at that video first to have a general overview and understanding of the whole process. This particular video, I'm going to walk you through when getting a real life, a real world data set, how can we deal with it? How can we program to do some coding to analyze the data to actually build the model and to predict as a classification or regression problem. In this particular demo, I will use a very simple data set that I extracted from the UCI data repository. It's a breast cancer data set. So this is a public data set you can get. Also, I posted a link in the other video as well. Is UCI data repository. They has a lot of public data set and that can be used for testing machine learning methods and compare different methods. Okay, and if you look at that, this is their web page. And I choose the particular popular one. This is their popular data set since 2007. And I chose this one, it's breast cancer. When it has a relatively large number of instances, like 569 instances, with also relatively large features, like 32 attributes, actually only 30 features. One of them is ID, the other one is the label, benign or malignant, cancer or normal, okay? The other 30s are actually the features. The features are listed here as described here. It was extracted from images, computed the measurements from the cell nucleus. I guess it's a histopathology image, and it measured the cell nucleus, the radius, and some textures, and the parameter area and smoothness, compactness, and so on, and fractal dimension, symmetry. Basically extracted, design some handcrafted features extracted from the image to form a set of features. There are 10 of them, but there are 30 features. 10 of them are the mean measures of these 10 measurements, and the second 10 measurements are the standard error. And the last 10 are the worst measures, either the min or max. Okay, so we end up with 30 measurements and like 30 features. Obviously, there are some correlations between the features. So let's see how can we deal with this with some methods, or some visualization method, some analysis method. In this particular case, I'm going to use Jupyter Notebook. So as an illustration, because it's quite good for interactive, show you the result and modify the coding so you can directly see the result. Okay, so I started Jupyter as a new notebook, so we can rename it first, save as demo, WDBC. So that's the name of the data set. So if we save it, that's our name. So I'm going to copy paste block of code and explain what it does that I did previously. So firstly, I will just introduce this. Okay, so I'll add some markdown thing here. So indicating as a markdown. So this is just the description of what it is. What is the data set? And it is a binary classification problem. You have 30 features, and you have the label is either malignant, which is cancer, or benign, it's a non-cancer. And we have in total of 569 samples. So then we're gonna load the data first and then see, we'll walk you through how we do that. First of all, we need to import some libraries. So with this, okay. So normally we are using pandas and to do some data science project, and you can load the CSV files or other type of data sets and do some simple analysis. And also one useful one is this Skype and some basic statistics methods in there. And more importantly, you have this Sklearn, where all the machine learning models and methods and evaluation methods and are included, built in. So it's quite handy to have those, so you can directly call the functions. This is also one of the reasons why we use this Python-based programming environment. Equally, you have R or MATLAB. They all have similar built-in functions. You can do similar things. Here, we just walk you through the basic process and see how normally I analyze the data when I firstly get the data. What are the tools available to do so? Okay. So that's the first task, import the libraries, necessary libraries. And we may also import some other libraries later when we need them, like the PCA, principal component analysis, and some other models, libraries later. And the next thing is to load the data. If I execute it, run it, I will go to the next cell. So then I'm going to use the Panda library read CSV to load the data. So where I save the data in my D drive, I can open it for you so we can have a look at the data. It's always good to have a look at the data yourself in the spreadsheet manner. So you can see this is the spreadsheet. The first column is the ID, which is less important in this case. And then the second column is the diagnosis outcome. So either malignant or benign. Okay, M is malignant, B is benign. And then we have 30 features. So radius, the mean value of the radius, and texture, mean value of the texture, and so on. All these 10 different measures. And then repeat the same measurement, but this time is the standard error represented by SE. Okay, and then another 10. And finally, the final 10 is the worst values of again, the same 10 measurements. So you can see those are the features. Then we have multiple, the row representing different instances. Okay, so here's the data set. We're gonna close it. Save. Then we can load it. If I run using this command, we can load the file, and use this command. We can show actually some of the example data, the first 5 rows, diagnosis, the feature name, and the feature values. So we know we successfully load the data. Good, that's a good starting point. Then next is we're gonna remove the ID because we're gonna extract the numerical values only. So next thing is we're gonna drop the column of the ID, then show it again. So you can see now with the ID column has been removed from the data. Okay, just some normal process procedures. And next one, what we can do is to also understand the data itself a bit more. If you use the .info function, So we can have some analysis in indicating how many instances per feature, and also the data type. In this case, for the diagnosis outcome is the object, and others are float 64. So it's like numerical values, continuous numbers. It is quite useful to look at this. Some of them could be categorical, and some of them could be others, like Boolean. So you need to have a look at these particular different types. This is related to how we select the feature selection methods and how we select the model to actually build the predictive models. So it's always good to check the data type. Okay, and also you can have an understanding of what features, what are the names involved. So have a look at this. This could be very useful. And the next thing we can also do is to describe some statistics of the data of the feature using this describe function here. So we calculate for each of the feature, we can have the count, how many, what is the number per feature, and also what is the mean, standard deviation, minimum, 20%, 50%, 70% value range, and the maximum values. You can see, in this case, you can look at their value range. Some of them are between 0 and 1. Some of them are pretty large, like the area. Okay, it's pretty large, a few hundreds, and some of them is only 0.09. Okay, so it's quite handy to look at some statistics of the feature value range as well. This is some useful things. And another thing we can also check is to count the number of classes or the outcome labels. So you can see in this case, this diagnosis is the second column, is the output label, is outcome events we are cared about. And we can count how many of them are benign or malignant. So it's like 2 to 3 ratio. It's not too bad. Some of the data we will find probably only 10 positive case and against 100 or even 1,000 negative case. So in this case, you need to be careful about when you do cross validation. You need to make sure there are certain labels distributed across the groups. Otherwise, your evaluation may be wrong. Okay, so it's always good to check also the labels and also the distributions and numbers of the labels. Okay, and also we can do a box plot. And just to show you all the very good tools that I normally use to check the data when I first use it. Not necessarily all of them are useful, but I'm just want to show you potentially it could be very useful either to show the numbers or do some visualization if you want. Using this tool as well, you can do a bar chart showing the counts for a particular case, the malignant and benign. Okay. And another useful one, firstly, we'll look at the statistics, and actually we can also do a box plot for each of the features using Boxplot. It takes some time. Okay, so you can see that for each of the features, like the radius, texture, I can plot all the value range in the Boxplot. In this case, I can look at the outliers. All the circles were classified as outlier, and the majority of the numbers are here. Pay attention here, the outliers may not be wrong. It could be reflecting the real cases. We are not necessary to exclude them. But if you look at this range, if you find a particular number is extremely high than other numbers, for example, a lot of the numbers between 0 and 1, then you have numbers that giving you 999. It must be wrong with that number. In that case, you should exclude that number. So this box plot is very good and handy tool for you to check whether there are some true outliers you need to exclude from your data. It helps for data cleaning. But in this case, I think the data set's already been cleaned, and we don't know the details of the clinical problem what their measurements are and the true measurements are. But actually we can do a quick check and to see whether there are particular number values or points that outside the range, significantly outside the range. Then we may need to remove it. But in this case, I think we are good. Okay. Well, for example, this one, you have a 500, a few 500 case, but you have quite a lot of points around the 200 region. But it could be really these two cases are in a very large area. That could be a real number. So in this case, we do not remove this. Okay, it depends on the problem. But you can see how we can use this box plot to look at the value range. And also, if you want to compare the value range, here's the function you can use. Do a subplot and box plot, and we can compare all the value range here across different features. You can see the radius mean. Here I only plot the previous 10, and you can also do the remaining 20 and 30. You can see there are particular features that have a really large values for the area measurements. Others are they pretty low, under 500. Like I mentioned in the previous video, it's always good to normalize the data because some of the machine learning model is quite sensitive to the value range. So in this case, we're gonna, before we do the modeling, we need to normalize the data, which I will show you later. Okay. And also another thing, there are so many tools you can visualize the data to understand the data first. Here is another one, which is also a box plot. What you can do is you can compare the value range and one box plot for the malignant case, one for benign case for each of the features. So you can see whether each of the features and have already can distinguish between the malignant and benign. For example, if you look at this particular feature, the radius, it's the benign case. Using this radius measure, the benign case and the malignant case can be separated quite well already. Look at the box plot here. Okay, so the malignant case normally have a larger radius and also larger areas and larger parameters. And so you can see a lot of these features are already quite good to separate the malignant and benign. So it's quite promising if we use some of these features. But in contrast, the fractal dimension may not be the case. For example, the malignant case kind of contains the value range of the benign case. In this case, may not be a very good feature. And also the texture, they are not separating from each other. Okay, so it's quite good way of have an initial understanding of which feature could be useful, which feature is not. Okay, using this box plot. Also, obviously, you can do some statistical tests like t-test where Wilcoxon sign rank test and to see whether it is significantly different from each other. Okay, so there are tools available to do the calculation as well. Okay, another one is also quite useful to look at the feature correlations. Is using those lines we can plot, we can look at the correlations between pairs of features. Okay, it takes some time to generate this because it's doing pairwise correlations. And then we have this fancy table being generated here. The number here representing the correlations. The higher is value range is between -1 to 1. 1 means it's perfect correlated, almost the same measure. Normally, you have vertical is representing the features, and horizontal is representing the same sets of features. And for example, you have obviously a very high correlation along the diagonal line, which didn't show here. It's supposed to be all ones. But if you look at this particular one here, if I can zoom in, no, the figure won't let me zoom in. It's just the text. But if you can see, or you can do on your own computers, if you cannot see it clearly, you have a very high correlations. For example, the perimeter is highly correlated to the radius. It's almost 1. And also the area is also highly correlated to the radius. It's 0.99. It's quite good, highly correlated. Maybe you will only need one of the measures in our model building if they are highly correlated. Okay. And some other features, they are in the middle range, like between 5 and 0.75 range. Also, some of the features are correlated. You can spend more time on looking at the correlations between each pair of features, and some of them are negatively correlated as well. There are some negative numbers as well. Okay, have a look at this and think about what can you observe from it, from this above table. Okay, have a look at this. Next one, another useful one. A lot of fancy tools we can use to analyze the data. So I will make it smaller slightly. It's better. If I execute this one, it's basically generate a set of scatter plots. Okay, I will show you what it is. If it can generate the result in seconds, I think. Come on, pop up. Yeah, but so basically we can also do a scatter plot and comparing using pairwise features. Okay, it takes longer. Okay, here we go. So again, the vertical axis representing each of the features, and the horizontal is also the same set of features. Here I only plot the top 10 features. Otherwise, it's going to be huge. We can't see any of this. In the diagonal line, obviously, it's the same feature. It's just calculating the distribution of the malignant and benign. So if you see these two distributions are separating from each other, that's a good sign. So which indicating this particular feature is useful. It should be consistent with the story of the box plot. Okay, if you can separate the two, the malignant from the benign, then this potentially is a very good feature. Okay, so you can check this diagonal line, look at the distributions. For example, in this case, for the smoothness, the two distributions are overlapping from each other. So in this case, this feature may not be particularly useful. So you can consider removing them later when you build the model. And also similar things for this one. Symmetry, and also fractal dimension. Those are the features may not be very useful. Okay. And what are those other scatter plots? What are the points here? They are representing x-axis and y-axis representing two different features. For example, this figure representing using the radius and texture together. So then you have the malignant represented by the orange dots, and the blue dots are the benign case. You can see that using these two features, radius and texture, you can more or less very good separate the two classes in the very good quality. Okay, so in this case, also radius and texture together is very good feature. And same thing for others. If you look at particular scatter plot, if there are a mixture of the two classes, like this one, they're using symmetry and also smoothness. Basically, they are not very good two features. Even they are combined, they cannot separate the two classes very well in a linear fashion. Okay, so yeah, in this case, you can also consider probably not including the symmetry and the smoothness, or at least you are not surprised if we're gonna show some automatic way of selecting the features. So here is you just have a knowledge of what features could be useful, what could be useless. Okay, so at least by understanding these features at this stage, you will not be surprised if the automatic method removed some of these features. You can justify why it's been removed and how does it do a very good job? Does it remove some useful features? For example, if it remove area or radius from the features, you can see what is the reason. Why is it doing the right thing or not? It's like a check by understanding this, by looking at the visualizations using different methods. So it's kind of important to look at. Okay, so have your own time, take your own time to actually look at these plots and do some observations and see whether you can conclude anything from the scatter plot. Okay, now we're gonna do some task to actually do a modeling using some of the machine learning methods. So like I mentioned, they are in different, all the features, they are in different range. Okay, like the plot here. Where is it? This one. So the value range of these different features, they are quite different. And so the first thing to do is to normalize the value range. A very good one to try is the zero mean. Okay, you subtract it by the mean values and divide it by the standard deviation. So it's kind of normalize it this way by using this block of code here. So firstly, we want to X will representing the data. So the first thing to do is we drop the labels. We drop the label column, so we use all the features and save it to the variable X. And then we can normalize it. Here we can use a library called standard scalar, and it will use the zero mean normalization to scale this. We can show you what it looks like after scaling. If you compare with the previous plots, and here is all roughly centered at the 0 point level, and also have some negative and positive values. So it's more or less normalized in a similar range. Okay, it's kind of pretty important step. And next, we can do some further analysis. In the first video in the lecture, I talked about PCA. When you don't care about retaining the meaning of specific features, we can use PCA to reduce the dimensionality of the feature space. Okay, so here I want to show you how to use this Python package to do the PCA, to have some analysis to see whether it can do a very good job to reduce the dimensionality of the data. So first of all, we apply the PCA. Okay, run it, and to the data. So X contains all the features values, and we're gonna apply the PCA to here. And now it contains the most significant modes or important features. And here we just use two of them to see whether we can use only the top two significant vectors or feature vectors or modes, PCA modes, to separate the malignant and benign cases. Okay, here is just extracting the first two PCA modes. And then we're gonna visualize the data points using these two features, using this line of code. Did I execute it? I think I do. So if I execute this, you can see that by using the first PCA components, it already did really good job to separate the two classes, malignant and benign. Okay, so then you have option. You can use these two PCA components, or even 3 and 4. You can have a play with looking at different components, PCA components, but obviously the first few ones are the most important one. So then you have two options. One is to use these two PCA features to build your predictive model. Okay, in that case, and it also will work really good as well. You can see if you can draw a simple line across this one, you can do the separation between the malignant and the benign. Okay. Otherwise, we can still use the remaining features and use other feature selection method to select useful features. If you want to have a kind of interpretation of the features, what are the important features like the radius or textures or the parameter are important features, then we need to use some feature selection methods. Okay, let's look at some of these methods. First of all, what I want to show you is if I use all the 30 features to build a model, then what is the result? Then compare with if I select a very few of the features using feature selection and build the model, and what are the results to compare, to show you whether it is important to do a feature selection and compare with the result. Okay, here I will start to build a predictive model using support vector machine kernel SVM. Okay, using all of the features. Here is the code. So first thing to do is I want to extract the labels because previously we set all the feature values to X. Now we need the label name, and we need to convert the labels from the tags M and B to 0 and 1 to numerical values. So actually the models can only accept numerical values as a predicted outcome. Okay, in this case, we run this one to assign all the output events or labels to the variable Y. Okay, and then we can do, we need to split the data because in total we have 500 each or 600 each data instances. But we were to train and validate machine learning model, we need to split the data into training and test. And most of the cases, we also need the validation if we need parameter tuning. In this demo, I just want to show you, and we split this into training and test for to save some time. Okay, but also you can do a validation set to do parameter tuning and to optimize the predictive models. Okay, here I can use this line of code to split the data X, S, and Y into training and testing. And 30% of the data is for test, and 70% is for training. Okay, if I execute it, it should split the data, so I can use X as train and X as test to train and test respectively. Okay. Now is easy task. Just use some built-in functions of SVM classification. SVM can also do regression, but here we use SVM classification. It's called SVC. To based on the training model, you can see that we feed a model between X as train and Y train. Y train is label, X as train is all the 30 feature values. Okay, and then it's finished. Let's then do a testing on the test data set. Is this line here. So the input will be the X as test, so which is the 30% of the data for testing, and Y test is the result, so we can know that whether our output is correct or not. If I run it, you can see the classification accuracy is 95%, which is not bad at all. Okay, so far we split the data into two sets: 70% for training, 30% for testing, and achieved 95%. But normally in machine learning method, if you look at the papers, and a lot of process requires, and we can do a cross validation, which is a better method to have an overall picture of the whole data set. In this case, if you only use 30% of the data for testing, you only have the result for 30% of the data. But then if we use cross-validation, we can have the result for all the data, alternate the training and validation and testing sets. Okay. In this case, I will show you a code to do 5-fold cross-validation. Obviously, that's easy to change to 3-fold or 10-fold. You just change this number here. Okay, and do a modeling using kernel radio based kernels, Gaussian kernels, to do the kernel SVM classification and calculating cross validation based on this 5-fold and print out the result. Okay, I run it. It's pretty quick. Actually, by doing 5-fold cross-validation, we can achieve a better accuracy of 0.97. In this case, you have actually more training data, like 80% of them for training, 20% of them for testing, slightly more data. So maybe that's why it's slightly better than the using 70% for training, 30% for testing. Okay, you can alternate this. For example, if I do 10-fold cross-validation and run it again, it's even increase the performance of 0.98. Okay. Obviously, a better option is to have some external validation sets. In this case, it's all coming from the same data set, so we don't have external validation sets we can test. But if your data allows to have some data acquisition from other institutions and provide to you, so reserve that set and train your model based on your own local data set and also test on this independent test data to check the generalizability of your machine learning model. That's a very good practice to follow. But here we just do a cross-validation, okay, as normally people do. But it doesn't mean it has achieved 0.98. It doesn't mean your model is good. You need to do an external validation, also check whether this model is overfitted or not. Now, let's try to select some features. Select some of the most useful features to do the modeling and see what is the result. Okay. So one of the popular method is looking at the correlations between different features. And there's a built-in function. I select k-best features and with Sklearn library. So here we just use that one, but you can read the documents to see what exactly it does. Here I use k equals to 3, so we simply, out of the 30, we only select the top 3 features and to do the modeling and see the results. And again, use 5-fold cross-validation and compare the results. If I execute it here, you can see this is the result of the 5 different folds, and then this is the average and standard deviation. So you can see that with only 3 features, top features, and we can already achieve 95%, which is not too bad compared with the 30 features. Obviously, the fewer the feature, the better. Right, you can avoid a curse of dimensionality and has a faster computational time, and so on. So really, this is a homework for you, and you can look at and keep getting. Currently, we selected 3 features. You can try 5 features, top 5 features, and top 10, and top 15, top 30, top 20, 25. And to see at which stage you can achieve similar performance or even better performance than compare with using all the features. Okay, as you previously observed, actually most of the features are quite useful, except a few of them, probably texture or symmetrics and smoothness. Probably 3 or 4 of them is not very useful. So you can see what are the remaining features, retained features, and to do the modeling. Okay, so have a play with this. And then we can do some evaluation matrices. Currently, it's only reporting the classification accuracy. And we talked about false positive and true positive and so on, and also precision recall and ROC. Now we're going to use the package to plot it. We'll see the result and compare the result in more details. So here we can generate a confusion matrix. The confusion matrix contains the true positive and true negative and false positives and false negatives. And then we're gonna plot and visualize the confusion matrix using this one here. So you can see this is this table here is the confusion matrix. You have the actual value and the predicted values, giving you the true positive and true negative, false positive and false negative, and so on. So you can see we only wrongly detected 8 of them, for malignant and benign case. And also you can calculate the precision and recall and also F1 score. Okay. And so by using those lines of codes, and you can predict this confusion matrix and calculate precision recall. And next one, we can plot the ROC curves using this one. Well, we got a warnings here, and basically we keep adding the plots on top of the same figure. So it's in the future version, it's not allowed. Every time you plot a new thing, it will create a new figure. So just to pay attention, but it's not a big deal for the moment. And here just for plotting the ROC curves. So this is the ROC curve, and every end of the curve is 0.98. The closer to the top left corner, the better. And this is the random line. You have the sensitivity and specificity. So yeah, in our previous lecture, we talked about how to look at the ROC curves. And so you can refer back to that bit and see what you can get out of these ROC curves. Okay, so far we've used the SVM to do the modeling, but there are other modeling methods like logistic regression, K nearest neighbor, naive Bayes, and the decision trees, and the linear discriminant analysis. A lot of those models we can use, and also this is built in to Sklearn, so it's quite handy to have. Okay, so let's try some of these methods. So firstly, we need to include the libraries, which is easy, just import the libraries, and also specify the model. We're gonna append all these different models and execute them in sequence, including logistic regression, linear discriminant analysis, KNN, decision trees, naive Bayes, and SVM again. So you can see that we didn't specify any parameters in those models, but there's a lot of parameters can be played with in each of the method. For example, KN, you need to specify how many neighbors you want to consider. Decision trees, you can specify how many trees and what the level of the trees and so on. Okay, a lot of things you can add and play with. This is one of homeworks that you can do. Okay, also for a support vector machine, you can specify different kernels and so on. And then we can evaluate this using, again, 5-fold cross-validation, split the data into training and testing, and calculate the result and compare the result of all these different models. Let's run it. It's supposed to be really quick, those methods. Okay, there's an error. Xtrain was not defined. Did I miss anything here? Where did I define the Xtrain or XXtrain actually? Okay, try it. Yeah, it's doing the drop. So there was a small mistake. I should use this normalized data. Okay. And okay, so here's the result. Based on the 5-fold cross-validation, we achieved 0.97 for the logistic regression, 95 for LDA, KN at 95. For the nonlinear model CART decision trees, actually it was pretty low compared with others, and also SVM. You can see actually a simple linear regression model achieved the best. But of course, bear in mind that we didn't tone the parameters. Probably you can use a shallower or less layers of trees and adjusting the decision tree parameters, you can achieve similar result. But in this case, it seems a linear combination of the features and could do the job in a pretty good quality already. So in this case, we may just use linear regression to do the job. Okay. And also we can do another box plot to compare the result and see the details of the run. So you can see this is the 5-fold different runs with the mean and LDA cards and so on, those different methods. Obviously, the logistic regression still achieve the best performance. It doesn't really the results are reliable and similar to each other across different folds. Okay. Then that's pretty much everything I want to cover. And finally, I will just type in a few questions or practice for you to solve, and I'll do a markdown. So, okay, so try to basically 3 practical things for you to try at home. So observe the results if we don't normalize the feature value range. So maybe some of the method doesn't work. Try to figure out what method which is sensitive to the value range. So remember to normalize it, or you can even try different normalization method like min-max. And also, second one is currently all the modeling methods, like I mentioned, SVM, KN, we didn't do any sort of parameter toning or changing the parameter to compare the performance, but you can spend your own time to try these different parameters. Okay, and maybe some of the methods even better than the logistic regression. And also, we currently use the correlation-based feature selection method, and there are other methods available, like filter-based one and a bandit one and other wrapper-based one. So a lot of different feature selection method is available in the built-in functions, and you can check and compare. And also observe the selected features by this automatic method, compare with your previous observations with the correlation matrix and also the box plot to see these selected features actually make sense. Okay, so that's it. Hopefully you can play, and the code of this of Jupyter notebook will be shared through the chat and available, make it available.